Okay, so section 10.2 is on trigonometric interpolation. And so we've done this before. We did this in chapter 4. We're going to do it again now using the discrete Fourier transform to obtain our trigonometric interpolant. And so if you consider a problem where we have data points that are evenly spaced, and we label our t coordinates t sub 0 through t sub n minus 1, and our x coordinates x sub 0 through x sub n minus 1. And we're going to discretize the t variable, so we're going to set t sub j equal to c plus j times a delta t, where delta t is equal to d minus c over n, or t sub n minus 1 minus t sub 0 divided by n. I've labeled c as t sub 0 and d as t sub n minus 1. And one thing to note, if we rearrange our equation for t sub j and insert what delta t is, if we actually solve for j, we have that j equals t sub j minus t sub 0 divided by, remember t sub 0 is c, divided by t sub n minus 1 minus t sub 0, and then times n. Okay. So now the discrete Fourier transform. So a recap of the DFT is that, well, very simply, y is Fourier matrix times x, and we have the inverse Fourier transform, inverse discrete Fourier transform, which is x equals inverse f times y. And of course, that the inverse of f is the conjugate of f. And so if we actually write out what the inverse discrete Fourier transform is, or if we write out the nice slick shorthand notation for it, it's x sub j, or this isn't a vector, I want this to just be the coefficients of x. So x sub j equals 1 over the square root of n summation k equals 0 to n minus 1 y sub k omega to the minus kj, where omega is equal to e to the minus 2 pi I divided by n. So now if we substitute this in to our formula, we have x sub j equal to 1 over the square root of n, sum from k equals 0 to n minus 1, y sub k e to the I 2 pi kj divided by n. So I've moved the I in front now. And so what is this? I mean, I noted what j was equal to, and so if we substitute what j is in terms of our t's and n, this equals 1 over square root of n, sum from k equals 0 to n minus 1, y sub k e to the I 2 pi k times t sub j minus t sub 0 divided by t sub n minus 1 minus t sub 0. And so this thing that's in parentheses is actually t minus c divided by d minus c. So this can be viewed as interpolation of the points t sub j, x sub j by the trigonometric basis functions, where the y sub k are the coefficients. Okay, and so I know this looks odd that we have complex variables here, but we can work with this to convert this expression to real form. So to do that, let y sub k equal a sub k plus I b sub k. And it turns out that by the discrete Fourier transform interpolation theorem, which I'll just state, label as theorem 10.6, we have that the interpolant, the trigonometric interpolant q of t, equals 1 over the square root of n summation k equals 0 to the n. So this is the form of the interpolant at this point, but just by substituting in what y is and by using Euler's formula to convert the exponential to sines and cosines. And so now if we do multiply things out here and combine real part and imaginary part, we get 1 over square root of n sum from k equals 0 to n minus 1. Now we have a real part. The real part is a sub k cosine of an angle 2 pi k times t minus c over d minus c, and then minus b sub k sine, and I'm just going to put an asterisk because we have the same argument that's in the cosine, and then plus I times, and this is all inside the summation. So let me make it clear that this is all inside the summation. And then we have, so plus I times a sub k sine of the same angle, and then plus b sub k times the cosine of the same angle. Okay? So here I've just split this up into a real part and an imaginary part. And, well, if x is real, the imaginary part of q, which the book calls I of t, is equal to 0. Okay? So, the coefficients, or the Fourier coefficients, a sub k, b sub k, are the coefficients of the trigonometric interpolant. Even more than that, though, we have, if we combine lemma 10, or lemma 10.4, and so I'm going to write down lemma 10.4. I did not previously write it down, so let's write it down. Lemma 10.4 states, let y be the discrete Fourier transform of x, then number 1, y sub 0 is real, and 2, y sub n minus k equals the conjugate of y sub k for k equals 1 through n minus 1. And if we combine this lemma 10.4 with lemma 10.7, I'm not going to write out lemma 10.7. It's simply just a trig identity under certain conditions. So combining lemmas 10.4 and 10.7, we get corollary 10.8, which simplifies Q even further. So corollary 10.8, and I'm not going to write down the hypotheses of corollary 10.8. Basically, it's for our data set that's evenly spaced, T sub j, X sub j, where the X sub j are all real, and we've computed the discrete Fourier transform of X to get Y and the coefficients of Y. We have the following result. So I'm going to skip the hypotheses and just write down that our trigonometric interpolant, P sub n of t, is a sub 0 divided by the square root of n plus 2 over the square root of n, and the summation goes from k equals 1 to n divided by 2 minus 1. And let me just note here in corollary 10.8, n is even. This is the formula for an even number of data points. So just notice that in the summation, we've basically kicked out the case k equals 0, okay? And we're also summing to half of n, and then minus 1. So notice we're only using half of the terms that were in q of n of t. So certainly this is, and so basically what happens as a result of lemmas 10.4 and 10.7, it turns out that the later trigonometric terms in the real part of q of n of t are redundant. So we don't need them, and we just use less. So this summation is summation of a sub k cosine 2k pi times t minus c over d minus c, and then plus b sub k sine of the same angle and then finally we add the term a sub n divided by 2, which turns out to be real as well, over the square root of n times the cosine of n pi times t minus c divided by d minus c. And so this is the trigonometric interpolant, and so this interpolant satisfies exactly what an interpolant should satisfy, which is that p sub n of t sub j equals x sub j. Remember, we're doing interpolating, so we want to go through the points t sub j, x sub j exactly. And so this is for j equals 0 to n minus 1.